Hello, this is Bashar Al-Bakri, and this is Lab 2 for Mechatronics ME411. In this lab, we are diving deeper into the ideas of circuits, and we're exploring more components, unlike the previous lab when it was simple components. In this lab, we are doing an RC and RL circuits and how we can analyze their behavior when we input a step function or a square function and a square input signal to it. Generally, RC and RL circuits are crucial to the mastering the concept of mechatronics because they can be used in filtering, timing, and energy storage in electronic signal systems. RC and RL circuits are essential building blocks in electrical engineering, and these circuits allow us to understand charge and discharge, time constants, which is a very important topic in this lab, and the relationship between voltage and current in reactive components. Well, the theory of the formulas that are embedded in this lab comes in the voltage across a resistor by using V equals IR. The voltage across the capacitor is found, which is the integral of the current and times the 1 over the capacitance. And the voltage across an inductor is found by the inductance times the differential, the derivative of the current function. And when we solve these, we solve them using Laplace transforms to make it easier to find the voltage of the capacitance with respect to the voltage source. We find this formula over here, and we end up finding that the time constant in the RC circuit equals T equals RC. And similarly for the RL circuit, this is the formula for the voltage in the resistor with the time constant being this. We built the circuit in Tinkercad, and these were the following values: 1 kilo ohms, 10 Henry, and 10 microfarad. The function generator generates a 5 peak-to-peak input signal with a frequency of 1 hertz, and we use an oscilloscope to measure the behavior. For the RC circuit, we use this formula to end up finding that the RC circuit the time constant by definition has to be equal to 1. In order for that to be the case, that means the time has to be 10 milliseconds. And once that happens, once we simplify the formula, we find that the voltage of the capacitor should be 3.16 volts, which means that we're gonna in order for our experiment to be successful, the voltage has to be 3.16 after 10 milliseconds of runtime. And when we run the simulation, after building this, we find out that it is true. After 10 milliseconds, the voltage of the capacitor reaches 3.16, which is consistent with the theoretical solution, which means our circuit was properly built and the wiring is properly built, and it was a good example. Similarly to the RL circuit, we're going to end up seeing that the time constant is also 10 milliseconds, and which means it has to reach 3.16 volts within 10 milliseconds. And in fact, the case happened as well, where in the RL circuit, this happened. In 10 milliseconds, it was 3.16 volts, which also means that our RL circuit was a proper circuit that was built properly, and the wiring was proper, and everything was proper. In conclusion, I believe that this experiment was really nice, and it opened our eyes to the idea of filters as well, because we took the voltage input of the voltage response of the capacitor and the voltage response of the resistor. I believe if we mix and match, we can find different behaviors. And this was lab 2, and thank you very much for listening.